Welcome back. In this video, we're going to try to introduce some other components. We've already talked about resistors, capacitors, and inductors, and in this session, I was hoping to talk about op-amps. And along the way, do a brief overview of time domain. How do you look at the signal in time domain? And how do you look at it in frequency domain, looking at transfer functions basically in the frequency domain. So let's go ahead and get started. A couple of things that I wanted to cover was one, if you look at the screen, you will see you see the libraries are listed right here where my mouse is moving, and that could you may not have it. If you don't have anything in it, simply click on this small icon here, and that gives you the option. Typically for beginners, the things you will use, definitely you will use the source, which is all the DC voltages and AC voltages. Most of the time we will use either DC voltage for just straightforward DC, or we're going to use the sinusoid. A lot of the work we're doing in the initial electrical engineering is going to be sinusoidal, so that's probably a nice place to go and use it. And then eval is some additional parts such as op-amps. You're going to find them in the eval library. So you just simply click on it, open it, and then get added to your list. I've already have my analog, which is the resistors, the capacitors, and that stuff. I've got my eval and I've got my source in here already. Okay, the first thing we want to do, we want to place it. One of the most common and the simplest of the op-amps we have is the 741. It's not very high frequency. It cannot react at the high frequency, but at the lower frequencies, anything below 100 kilohertz, that's just fine. So we're going to use it for some experiments here and just learn how the simulation works with it and how we put it in. So let's go ahead and find it. Since we know its name, probably the simplest way to do that is just go to the library and type in the beginning of the part's name, and it'll pop up and you can click on it and bring it in. And there it is. Before I get too far into it, let's go ahead and just zoom in on this just a little bit. And this is useful. I know these icons are relatively small, so you may not be able to see it, but there's an icon with a box over the magnifying glass. If you click on that one, then you can say how big your canvas should be. And I may want my canvas to, let's say, be that big for now. Okay, we can always change our mind later on. So if you look at this thing, you got the minus sign, and remember that the feedback always got to go to the minus. So that's one of the common mistakes folks make, is put the feedback to the positive side, which means the op-amp is always saturated, and it's no good to us. The other one is, for this one, we're now going to use the OS2 and OS1, which is the offsets 1 and 2. If you wanted to move your signal up or down, you could force it with these two. And as you remember from reading about op-amps and all of that, V plus and V minus are basically the two, the floor and the ceiling, if you want to think about it. The output can never go below V minus and never can go above V plus. They're called the bias voltages. Okay, so we got to make connection to everything. The only two that we can leave alone is OS1 and OS2. So one of the simplest amplifiers we can build is an inverting amplifier. So let's go and work on that just to get a sense of how should we set this up. So we need some resistors and we need some supplies and things like that. So let's start with the supplies. So I can go get to my source and find some DC voltage, DC, and there it is. I'll double click on it, and I need a couple of them, and I'm going to put them down here out of the way, and I will explain why I'm doing this. So I'll just put them right here out of the way. And I need two of them because I need a positive side, which is usually called VCC, and I need a negative side, which usually is called VEE. And these are after transistor, collector and emitter of the transistor. That's more or less where the names come from. And then of course you always need to ground your circuit. So as soon as I find there's the ground, and we're gonna get the grounding reference, and we're gonna put that one on this, okay, and put it on this one too. And we're probably gonna need one over here, so we'll just drop one in for the time being. All right, so the next thing I need to do is I need positive and negative just to be on the safe side. This 741 can't handle it. I'm going to come in here and I'm going to create a positive voltage and a negative voltage, and just let's say 15. We're going to make one plus 15, and we'll make the other one negative 15. Now I could draw a line from the -1 all the way up to the -1, and the positive one all the way to the positive one. But if you get a circuit with lots of these power and these wires for the bias going all over the place, it could get really confusing to keep track of what's going on there. So what we'd like to do is go ahead and use the port naming, and you can use any of them you like. I just use the first one. It depends on which way you want it to be oriented. So we're going to grab this one, and then we put one more here, and we just, this way we can name these things. So then anytime I need that voltage, I can come and use it. So let's go ahead and pull this up just a little bit. So we're going to call this one, I think that's the positive side, so we're going to call it VCC. So you always want to give them relevant names. So this one we're going to call VEE. Okay. Now what I can do is literally Control-C, copy paste. Basically, you can either right click on this, go copy paste, or if you remember, Control-C, Control-V does copy paste. So you just do the whole component, take it, put it up, and then this is the positive side, so I'm going to go put it on the positive side, and then I'll just want to be nice, so I just pull this up so it's just not in my way of that chip. And then VEE is the negative side. Do the same thing, Control-C for copy and Control-V for paste, and I'm going to take it up here and put it on this one, and don't want to get everybody down, just this one, just out of the way so we can kind of see it. This way is a little cleaner. That's all I'm doing, and I'm giving it a positive and a negative voltage. And then the next thing we know what we need to do, we're gonna I think I said we're gonna build a inverting amplifier with a gain of, let's say, 5. We can go back and do our analysis if you don't remember what it is, but the inverting amplifier is relatively simple. So what we're going to do is connect the positive side just simply to ground. So let's go ahead and do that. And then let's go ahead and grab some resistors. So we know resistors are all in analog, so we're just going to go grab that. There it is, double click on that. So I need a couple of them. I need one for the feedback, and so I'm going to put one down here for feedback. That should be enough. I think that's plenty. And of course, by now you know that you can, if you want it, you can click on this thing and rotate the resistor. Oops, I rotated the wrong resistors. So let's undo that one. So let's select this one and rotate it. Might look a little better if I do this. There we go. 1K is fine. I'm going to make this 5K just to have a gain of 5. If you recall, that's the feedback resistor over the input resistor gives me 5. So I can, and then, I need a source as well. So let's connect these wires, and then I'll go get a source. So this comes down, this is the output, and we'll bring it down, connect it here. This guy goes up here, and then, oops, I ran through it. So let's do this, and then back here. Oh, so that wasn't good. So what I need to do is do a little bit of a modification here. I could potentially take this one out a little ways, cut this wire, and have the feedback. The feedback has to come right here, and then I can put a source or something here to sense what. So what would be? So when you're using the source, I think one of the most useful sources we have is this one is sine, this sine one. The reason I'm saying that's a good one for us to use is because it allows us to change its behavior. Let's say if you're trying to do multiple things, in this case we want to do these, show you what happens in a simple DC or an AC put in there, and then we want to do a AC analysis for this particular part. This will allow you to set all kinds of values for it, so you can use it both in AC as well as as AC sweep analysis as well as the time domain analysis. So let's go ahead and grab this ground and finish the circuit before I get sidetracked. Okay, here we've got a nice circuit. It's got a 1K input resistance, incoming resistance, and then it's got a 5K feedback, so we know the gain is going to be 5. We've got a nice output coming out of here, so that's all good. And then we've got our VCC and VE connected to pin 7, which is the positive side, and pin 4, which is the negative bias voltage. We build an inverting amplifier, so when we look at it, it's going to be 180 degree out of phase. Therefore, the AC for the DC really doesn't matter. So let's kind of go through and do that. We're going to start with the simplest case. If you look at this thing, this part has a number of different parameters you can set. The offset is just simply a DC offset. Now, if you want to set a DC, just set this one and set the amp and the AC to 0, and it acts like a DC voltage if you wanted to. For now, for us, we're just not very exciting to look at a DC. We're going to set the DC offset to 0. Oops, they don't want to do that. Undo it, move it back down. Okay, so the amplitude is basically doing the magnitude of the cosine. What's the peak of the sine we are creating? So for our case, just for simplicity, we're going to say this is 2 volts. Okay, and then frequency, we'll just set it to 1 kilohertz, and that's fine. AC, so this is kind of interesting. Now we already know about the amplitude. This AC value you can use, pretty up to you how you want to put it in. I'm going to put a 1 in here for the time being. What it's used for, when we do an AC sweep, it just runs it at this level. And remember, it's a ratio of output to input that we are interested when we're doing AC sweep across the frequency. So we have to give it the nominal value to start. This value will have no impact when you're doing a time base or time domain analysis or a time series sweep on the circuit. Only comes into play when you do a frequency or AC sweep on your circuit. So this is a simple, we finally got to a place, hopefully everything is right, everything is connected. One of the most common things you're going to run into is some of the wires may not be connected, or things of that nature. Other than that, this should be ready to go. Let's go ahead and go to PSpice. Let's go ahead and edit it. I don't know what I have, but you can either create a new one or edit one. I'm going to do a time domain first. Take a look at time domain. I'm going to run it for about a second, and then I'm going to say do steps at 10 microseconds. If you make the steps really small, it's just going to take you a long time to do it, but you get a much nicer and smoother curves come out, data plots that comes out. So that's good. So remember that V3 is this input voltage for this thing, and this V out of U1 is the output. So just remember that, because we're going to need that in a minute. So we're going to apply this. This was the simulation. We're going to apply it, and all is good. Okay. And so now what we're going to do, we're going to run it. You can either go to PSpice and hit run, or you might as well just click on the yellow arrow, green arrow here, and runs it. Okay, it runs it. You can use the probes to figure it out, or you could just come into the trace and say I want to add traces, and you say what do you want to see? Well, I want to see what I put in, which is V of the plus side of V3, and I want to be able to also see V out, right? So I want to see those two things. So you say, okay, and by the way, before I forget, there's a whole bunch of math you can do on this data if you want to convert them to something or do other things with it, all available here if you wanted to. But for now, we just want to look at input, which was we called V3, and output, which was out. Ooh, okay, so because our frequency is 1 kilohertz, we're looking for a second. We got thousands of cycles in there. And once again, if you go to the zoom and just take a cut a small piece of it, so we can kind of look at it, just a few cycles. Oh, that's more than a few cycles. So let's do a little. So we're gonna maybe this much. Oh, here it is, and you can kind of see the peak to peak. Green is the input, and red is the output, and you can see is the input is 1 and output is 2, 3, 4, 5. Gain of 5, everything is good. And the other thing you notice, the peak, look at where this is, and this is the 180 degree out of phase. Okay, it's an inverting amplifier, right? That's what it means to be an inverting amplifier. One is minus the other. Okay, so that was a time series analysis, and that was really nice, and I can look at both of them in time domain, see what the input is, what the output is. Now let's say I want to look at this thing on a frequency domain, and I want to look at basically across a range of frequencies. This is only looking at it at 1 kilohertz, what we set it to. So what if I want to look at this signal not just across time but across frequencies? So all you have to do now, the circuit is all set up, we'll come to PSpice and we say, okay, edit my simulation. I don't want to be in time, I want to do AC sweep, which basically means change the frequency that I tell you. I'm telling them to start at 1000 hertz and stop at 5 meg. Let's go to 10. What the heck? That makes it not too hard. 10 meg, and now 10 points per decade. Again, if you put a large number in here, it's gonna take a long time. If you put a small number, then you can get done faster, except your curves got a little jaggedy on it. Now, it's an AC sweep. I can do linear, I can do logarithmic, and so I put it at logarithmic because you can put it at linear. It really doesn't matter. It depends on what it is you're looking for. General setting, AC sweep. That's the only thing I'm going to change. Where to start, where to end, and let's then we're going to apply. Okay, and we're going to say okay, and let's run it. Okay. So now when I'm here, I can actually come in. Now guys, notice what the x-axis is, or the horizontal axis. Now it's in, I started at 1 kilohertz. That's what I tell him to do that. And I told him to stop at 10 megahertz, and that's exactly what he did. And if you notice, these are all in logarithmic scale. You see that from 1 to 10k is the same size as 10 to 100. As 100 is to a 1 meg, which is great. Okay. Now, what is it I want to look at? Well, let's go to the trace and say, let's go ahead and add a trace. And this time I want to see the gain. I want to see the ratio, the H of S in a sense, right? The transfer function, not quite, but at least V out over V in. I know V out is this guy over / divide. And then I think V3 was the input, so out over input, so I'm seeing the ratio, so I'm going to plot. Oh, there it is. That looks a lot like it. And then you say, wait a minute, this was not a low-pass filter. This was just a simple gain. Why isn't the gain not staying flat? The gain actually starts pretty nice. Oh, and this is a very useful thing. This cursor is very useful. You can do the cursor, and then as your cursor moves, you can kind of watch what's happening, what frequency you're in, what values you're reading. It's pretty cool. Anyway, so as I move down, you see that the gain really drops off starting around 100 kilohertz. That's why they say 741 is only good up to 100 kilohertz. After that, the gain really kind of take a nosedive, and when you go right about a megahertz is at 0. You see that? So that's great. So now we've looked at a AC sweep, we've looked at a DC sweep, and all that. And we've also learned that the 741, by its very nature, is a low-pass filter. It just basically, it'll start losing gain at around 100. Well, it looks like it might be even earlier. It looked like you start losing it around maybe 50-ish, 50 kilohertz. And then as 100, it becomes really noticeable because it's getting pretty close to the -3 dB half power, and then rolls off. By the time you get to 1 megahertz, it really has no gain. It's up to 0. Okay, that brings us to the end of this particular presentation. So just to recap what we've talked about, we started by talking about this basic op-amp. Other op-amps are very similar to this one. We talked about setting up the plus and the minus voltages, using the ports instead of drawing a line to keep our schematic clean. Then we talked about the fact that when you set up your simulation, you can set up your simulation either as AC sweep if you want your horizontal axis to be frequency, or you can set it at time domain, which makes the horizontal axis time in seconds, or whatever units you're using. So those are the two very good and useful ways of characterizing inputs, outputs, their relationships, and things of that nature. Thanks for listening.